and welcome back to Sudoku Swami's pencil and paper method. In the last two lessons, we talked about all the different ways that singles can show themselves and the conditions that create them. So today, before we solve our puzzle, we're going to take the next step up and talk about what are called locked candidates. We're going to start by learning about how locked candidates work when you are using a computer or smartphone app that features full-blown, automated, and complete candidate lists. This will help you better understand how we're going to apply them to pencil and paper puzzles, okay? Here we go. There are two conditions that create locked candidates. First, there must be 2 or 3 instances of the same candidate appearing in the intersection of a row and a block or in the intersection of a column and a block. And then second, they must be the only instances of that candidate in either the row or the column, or they must be the only instances of that candidate in the block. So let's take a look at what this means. Up here we have the intersection of row 3 and block 2. And down here we have the intersection of row 8 and block 7. In each case, the 3 adjacent yellow cells are the intersection cells. Each group of 3 cells lies in 2 houses at the same time. Those 2 houses overlap to form a 3-cell intersection. So the first condition for locked candidates is that there must be 2 or 3 instances of the same candidate in one of these 3-cell intersections. And as you can see up here in row 3, we have 2 instances of candidate 9, and the other cell of the intersection is blocked by this 5. So there is only room for 2 candidate 9s. And down here in row 8, we have a candidate 7 in all 3 of the intersection cells. So now let's consider the second condition for locked candidates. Let's say we have a few other candidate 9s in block 2 like this, and let's say there are no other 9s in row 3 outside that block. There must be a 9 placed in row 3, and since the 2 9s in the intersection cells are the only 9s in that row, we know that one of them must be true, right? They are a conjugate pair. One must be true and one must be false. This means that any other candidate 9 in that block must be false and can be eliminated. Let's color them red to indicate that they are false. And the corollary to this is that if there are a few other candidate 9s in row 3, but there are no other candidate 9s in block 2, then it's the same thing in reverse. There must be a 9 placed in block 2, and since the 2 9s in the intersection cells are the only 9s in that block, we know that one of them must be true. Again, they are a conjugate pair, but this time they are a conjugate pair with respect to the block instead of the row. Nevertheless, one must be true and one must be false. This means that any other candidate 9 in row 3 outside that block must be false and can be eliminated. And again, we'll color them red. All of those red 9s are false. The reason these are called locked candidates is this. If there are no other instances of that candidate in the row, then the 2 candidate 9s in the yellow cells are said to be locked into the block, meaning that one of them must be true within that block, which further means you can eliminate all other instances of that candidate within the block that are not in the intersection. And if there are no other instances of that candidate in the block, then the 2 candidate 9s in the yellow cells are said to be locked into the row, meaning that one of them must be true within the row, which further means you can eliminate all other instances of that candidate in that row that are not in the intersection. Got it? All right, now let's look at row 8. This time we have a candidate 7 in all 3 intersection cells, but the concept is the same. If there are a few candidate 7s in block 7 and there are no other candidate 7s in row 8 outside that block, then we know that one of those 3 7s in the intersection cells must be true, right? There has to be a 7 placed in row 8, and the only 7s in that row are in those 3 yellow cells. So one of them must be true. But this time, because there are three of them, they are not a conjugate pair. But still, the fact remains that one of them has to be true. This means that any other candidate 7 in that block must be false and can be eliminated. And again, the corollary to this is that if there are a few other candidate 7s in row 8 outside that block and there are no other candidate 7s in the block, then again it's the same thing in reverse. There must be a 7 placed in block 7, and since the 3 7s in the intersection cells are the only 7s in that block, we know that one of them must be true. This means that any other candidate 7 in row 8 outside that block must be false and can be eliminated. So you see, this works either way regardless of whether there are 2 or 3 instances of our candidate in the 3 intersection cells. But as you may recall from lesson number 6, we won't be filling in locked candidates unless they are a conjugate pair, i.e. when there are only 2 possibilities. When there are 3 possibilities, like you see here in row 8, we will just make a mental note of it without actually filling them in. This will help save time and help keep the puzzle cleaner looking and less cluttered. And of course, these same rules apply to the intersections of columns and blocks like this. Here in this diagram, on the left, we have the intersection of column 3 and block 1. And over here on the right, we have the intersection of column 8 and block 6. And as you can see, up here in column 3, we have 2 instances of candidate 5, and the third cell of the intersection is blocked by this 9, so there is only room for 2 candidate 5s. And over here in column 8, there is a candidate 1 in all 3 of the intersection cells. So if we have a few other candidate 5s in block 1 and no other 5s in column 3 outside the block, then we know that all of those red-colored 5s in the block are false, because one of the 5s in the yellow intersection cells must be true in the column. And the corollary to this is that if there are a few other candidate 5s in column 3, but there are no other candidate 5s in block 1, then it's the same thing in reverse. We will know that all of those red-colored 5s in the column are false because one of the 5s in the yellow intersection cells must be true in the block. And over here in column 8, if there are a few other candidate 1s in block 6 and no other 1s in column 8 outside the block, then we know that all of those red-colored 1s in the block are false because one of the 3 1s in the yellow intersection cells must be true with regard to the column. And the corollary to this is that if there are a few other candidate 1s in column 8, but there are no other candidate 1s in block 6, then it's the same thing in reverse. We will know that all of those red-colored 1s in the column are false because one of the 3 candidate 1s in the yellow intersection cells must be true with regard to the block. And again, you can see that this works either way regardless of whether there are 2 or 3 instances of our candidate in the 3 intersection cells. Now, if there are other instances of the candidate in both the row and the block like this, or in both the column and the block like this, then the 2 or 3 candidates in the 3-cell intersection are not locked and no conclusions can be drawn. And that's it. That is how locked candidates work. It's funny, but when dealing with locked candidates in a pencil and paper puzzle, the process of deduction is backwards from what it is when you are using a computer app and can see all the candidates. It is deductive reasoning either way, but with pencil and paper, the reasoning goes in one direction, and with computer apps, it goes in the exact opposite direction. Let me show you what I mean. Here in this puzzle, let's highlight the candidate 4s. Up here in block 2, these are the only 2 4s in that block, so one of them must be true, and that means these 3 4s in row 2 outside the block must be false. So we know that because one of these 2 4s in block 2 must be true, a 4 cannot exist anywhere else in row 2. And likewise, if we highlight the candidate 8s, we can see that these 2 8s are the only 2 8s in column 2, and they both lie in block 1. So one of them must be true, and these other 4 8s must be false. So because one of these two 8s in column 2 must be true and they both lie within block 1, we know that an 8 cannot exist anywhere else in that block. But with a pencil and paper puzzle, the logic goes something like this. We say that because there is a 1 here and a 1 here, a 1 cannot exist in these 3 red cells, therefore there must be a 1 in one of these 2 cells. And likewise, because there is a 7 here and a 7 here, there cannot be a 7 in any one of these 5 cells, therefore there must be a 7 in one of those 2 cells. And again, because of this 9 here, there cannot be a 9 in any one of these cells, so there must be a 9 in one of these 2 cells. So you see, the logic is backwards. With a computer app, you start out by saying that because these candidates are true, these other ones must be false. And with pencil and paper, you are saying because a candidate cannot exist in these cells, it must exist in these other cells. And again, because there is a 9 here and a 9 here, there cannot be a 9 in any one of these cells, so there must be a 9 in one of these 3 cells. But as I mentioned earlier, we will only be entering locked candidates when they are a conjugate pair, i.e. when there are just 2 candidates in the intersection and not all 3. This way, as soon as we discover that one of them is true, then we will know that the other one is false. And if we discover that one of them is false, then we will immediately know that the other one is true. And lastly, one cool thing that happens quite often is when we have a set of locked candidates that are perpendicular to another set like this, where a conjugate pair is kind of pointing at one of the candidates in a perpendicular conjugate pair. Because one of these 2 candidate 2s in block 7 must be true, we know that this 2 up here in row 1, column 3 cannot be true. The group of 2 that is kind of pointing at one of the candidates in the other pair will always negate that single candidate, and thus we will immediately know that the other candidate in the perpendicular pair is true. Think of it like a ray gun, where the 2 candidates are zapping that single candidate. And even if this conjugate pair up here is on a diagonal, this is still going to work. One of these 2 2s must be true, so this 2 has to be false. So we can immediately erase this red-colored 2 and enter this 2 over here. However, the set of 2 pointing candidates cannot be on a diagonal. They must either be in the same row or the same column in a straight line, like this. One of these 2 5s must be true, therefore this one must be false, and that means we can erase that red one and enter this one. Got it? All right, now let's solve today's puzzle. Okay, we've got 25 givens, and there is nothing particularly special about this puzzle, except that I hope it will demonstrate many of the concepts we have learned in the past couple of lessons. I would say this puzzle is a little bit harder than it might look at first glance, and I'm sure if we solved it 10 times, we'd probably end up doing it differently every time. But let's just cycle through the numbers and see what happens. So there are 3 1s. We've got one here in row 7 and one here in row 9, and that means we can enter a conjugate pair in those 2 cells. One of those 2 candidate 1s must be true. They're the only 2 places left in that block for a candidate 1. And up here we've got another 1. So this one down here blocks column 4, and this one up here blocks row 2, so that means another conjugate pair of 1s can go right there. Does everybody see that? All right, now there are only 2 2s in the whole puzzle, and they are right there, and they block columns 2 and 3. So that means a 2 must go into one of those 3 cells, but that's not a conjugate pair, so we're not going to enter that. We'll just make a mental note of it and move on. Now there's only 1 3 in the whole puzzle, and that's right there, and there's not much we can do with that. So let's move on to the 4s. We've got a 4 here and a 4 here, and this one blocks row 3, and this one blocks column 8. So that means we can put a conjugate pair of 4s into those 2 cells. Now one of these 2 4s has to be true, so there can't be a 4 anywhere else in column 9, and that means down here in block 9 we can put a conjugate pair of 4s in these 2 cells, because this 4 and these 2 4s up here block those 2 columns, column 8 and column 9. So now let's go to the 5s, and because of these 2 5s right here, we can put a conjugate pair of 5s in those 2 cells. And because of these 2 5s in column 7 and column 8, we know there must be a 5 in one of these 3 cells, but again, that's not a conjugate pair, so we're just going to leave that blank. So let's move to the 6s. So we've got a 6 here and a 6 here, which means a conjugate pair of 6s can go into these two cells. Now notice that this cell is not a bi-value cell. There are only 2 candidates in that cell, but this cell could also be a 2 or a 5. But we're only entering conjugate pairs, so we know one of those 2 cells has to be a 6, and one of these 2 cells has to be a 1, and that's all we know right now. And now because this 6 blocks row 8 and this 6 blocks column 7, we know that a candidate 6 must go into those 2 cells. Those are locked candidates. One of those 2 cells in that block must be a 6. And now because these 2 6s rule column 8 and this one rules column 7 and this 6 rules row 5, we know a 6 must go into one of those 2 cells. And that looks like all for the 6s, so let's move on to the 7s. If you remember from the lesson on singles, we have what's called a foursome on the 7s. These 4 7s interact with block 7 in such a way that there is only one cell left for a 7 in that whole block, and so we can enter a 7 into that cell. We have 2 columns and 2 rows, all containing a 7, intersecting with block 7, leaving only one place left for the 7. And now because of this 7 in row 4, and this one in row 6, and this one down here in column 4, we know we can enter a 7 into this cell. That is a hidden single. And now that we've entered that 7, we can enter a conjugate pair of 7 into those 2 cells and another conjugate pair of 7s into these 2 cells. Now because one of these 2 7s up here in block 2 must be true, and one of these 2 7s up here in block 3 must be true, the only way that's going to work out is if this 7 and this 7 are true and these 2 are false, or the other way around. This 7 and this 7 will be true and these 2 will be false. That's the only way it can be because those are 2 conjugate pairs in the same 2 columns and same 2 rows. Now this is called an X-wing because the relationship between those 4 candidates kind of resembles an X. And because of their relationship, as soon as we determine the true-false value for any one of those 4 7s, we will know the true-false value of the other 3, because we know that only 2 of them can be true and the other 2 must be false. Now another thing you want to do as you're going through the numbers is you want to check each block and see if that number is accounted for in all those blocks, and if it's not, then you want to try to see if you can put something in there, either entering a number or some candidates. So in block 1 we've got a 7, in blocks 2 and 3 we've got our X-wing, and then we have 7, 7, 7, and then 7, 7, 7. So all the 7s are accounted for and we can move to the 8s. So because this 8 up here blocks row 1 and this 8 down here blocks column 3, we know we have a conjugate pair of 8s in block 1 here on a diagonal. One of those 2 cells must be an 8. And then because of this 8 in column 5, we know we can put another conjugate pair of 8s in these 2 cells, and notice that we have a ray gun. Because one of these 2 8s must be true, we know that this 8 cannot be true. Okay? So you can eliminate that one and enter this 8 as the value for that cell, and that cell is solved. And now because of this 8 in row 9 and this one in column 5, we can enter a conjugate pair into these 2 cells, and so now those 2 8s in row 8, they rule that row, so there can't be another 8 in that row, and there can't be another 8 in row 9 because of this one, and there can't be another 8 in column 7 because of this one up here. So we know we can solve this cell for 8. So that means you can erase that candidate 6, and because this was a conjugate pair, you can enter that 8 and enter that 6 as the solutions to those cells. Now look what we have. We have a naked pair of 8 and 6 in column 9, and that's because we have a 6 and 8 in row 5, we have a 6 and 8 in column 7, and we have a 6 and an 8 in column 8. So these 2 cells are indeed bi-value cells. That is a naked pair. One of those cells has to be solved for 8, and one of those cells has to be solved for 6. Okay? So now let's check all the blocks for 8. We've got an 8 in block 1, we've got the conjugate pair in block 2, we've got the 8 there, we've got the 8 there, the 8 there, the 8 there, and the conjugate pair. The only place we don't have an 8 is here in block 4, and we can see that there is a conjugate pair in these 2 cells because all the other cells are blocked by this 8 in column 3, and this 8 in row 5, and this 8 in column 2. So now we have 2 X-wings on 8. We have one here in this middle vertical chute between those 4 8s, right? We know that one diagonal pair of those will be true and the other diagonal pair will be false, even though we don't know which is which yet. And then we have another X-wing on these 4 8s. Okay? So again, as soon as we know the true-false value of any one of those 8s in each group, we will know the value of the other 3 in that group. All right, that's all for the 8s, so let's move on to the 9s. So because of this 9 up here in row 1, we know there must be a 9 in one of these 2 cells. That is a diagonal conjugate pair. So now let's go back to the 1s. And because we entered this 7 a little while ago, we can now put a conjugate pair into these 2 cells on candidate 1, because this one blocks column 3, and these 2 1s, this conjugate pair on 1, block column 5. And once again, this cell here is not a bi-value cell, this is not a bi-value cell, and this is not a bi-value cell. However, these 2 cells are bi-value cells. They can only be 8 and 6. But these 3 cells with 2 candidates each up here are not bi-value cells. All right, so now at this point of the puzzle, it doesn't look like there are any other conjugate pairs for us to enter, so we have to look for something else, and I want to draw your attention to this cell right here. This cell can see a 1, a 2, a 3, a 4, a 5, a 6, and it can see this 7, and it can see this 9, but it cannot see an 8. So the only number that this cell cannot see is an 8. That means it is a naked single, and you can solve it for 8. But remember, this is part of our X-wing, so this 8 also must be true because that diagonal pair has to be true. So we can eliminate those 2 8s, and we can enter an 8 in each of these cells as the true value for both of those cells. And now let's look at this cell. This cell can also see a 1, 2, 3, 4. It cannot see a 5, but it can see a 6, and a 7, and an 8. As you can see, this 8 as well, and this 9. So that means this cell has to be solved for 5. Okay, that is a naked single. And again, in that same block, this cell can see the 1, 2, 3, 4, 5, 6, 8, and 9. So the only number that cell can be is a 7. That is a naked single. But don't forget, that is also part of our X-wing, so that means this 7 has to be true. That diagonal pair of 7s must be true. So you can erase that 7, and you can enter these 2 7s. Okay? And now we're going to start jumping around a little bit. If we look at these 2 5s, and now we have this 5 entered, the only place for a 5 up here in block 3 is right there. So you can enter that 5, and because that was a conjugate pair on 4, you can enter this 4 and this 5, all right? And now, because we've solved this 5, that means there can be no other 5 in row 1 and no other 5 in row 2. So this cell must be a 5. And since that is a conjugate pair on 9, you can eliminate that 9 and solve this cell for 5 and this cell for 9. And now you can see there are only 2 cells left in block 1, so they must be 4 and 3. That is a naked pair. And then, because of these 3 5s, we can put a 5 in this cell right there. That is the solution to that cell. And because of this 5 up here and this 5 here, we know that a 5 can only go into that cell. But now we have a conjugate pair down here in block 7, so that means this 5 cannot be true, and you can enter both of those 5s. All right? All right, so all the 5s are done and all the 7s are done, and there are a lot of things going on right now, so let's get to them one at a time. Let's take a look at these 2 6s down here in row 8 and row 9. There's only one place left in block 8 for a 6, and that's right there. That is a hidden single. But don't forget, we've got a conjugate pair up here in row 1, so that means this one has to be false, and now we can enter those 2 6s. Okay? And now because we entered those 2 6s, we know that a 6 must go into one of these 2 cells, and now we have a naked pair on 1 and 6, and we have an X-wing on the 6s. So we've got an X-wing on the 6s, and we've got an X-wing on the 8s in that central horizontal chute. And next, there are only 2 empty cells in block 2, so they must be a naked pair of 1 and 2, and likewise, this must also be a naked pair of 1 and 2 in row 1, because the 4 and the 3 are taking up those 2 spaces, and there are only 2 places left. So now before we finish up here, let's go down here in column 6. This has to be a naked pair of 4 and 2 and 4 and 2, because that's 1 and 6 and 1 and 6. And then there are only 2 cells left in block 8. They must be 3 and 9. Okay? So the only value left for this cell here in row 6, column 5 is a 4, and we can enter that. Now we have an instance of what we call side hatching. If you remember from the video on singles, let's take a look at column 3. There are only 3 cells left where a 4 can go, okay? But because we have a 4 here and a 4 here, there cannot be a 4 in either one of those cells. So the only place in column 3 where a 4 can go is right here, and that solves that naked pair, 4 and 3, okay? And now up here in row 2, we have a full house. There's only 1 cell remaining, and that has to be a 3. And now this is something interesting that we'll talk about in a future video, but we have what's called a unique rectangle pattern here. This cell cannot be 1 and 2. Because if it was, that would allow for 2 separate solutions to this puzzle. And I'll explain that later, but just take my word for it right now. This cannot be a 1 or a 2. Okay? So that means the 1 and the 2 must go into this cell, which only leaves a 9 possible for this cell. And you can enter the 9 right there. And now we have another naked pair of 1 and 2 in column 8. And then over here in column 9, we have 2 empty cells, so they have to be 2 and 3 and 2 and 3. And we also have 2 empty cells in column 3, so they must also be 3 and 9. All right, before we go any further, I'd like to point out that there are 5 cells all containing 1 and 2 up here, and they are all connected in such a way that as soon as we solve one of them, we are going to know the value of those other 4 cells. And these are called remote pairs, and we'll cover this concept in a future video. But let's keep going. As you can see, I'm coloring the cells from time to time, but that's just to make things easier for you to see. When you're solving puzzles at home, you're not going to need to use any coloring, okay? All right, so because of this 9 and this 9, that blocks all the cells in block 7 except for this one, so that has to be a 9. That is a hidden single. But before we enter that, let's look over here. We've got our naked pair of 3 and 9, and once we solve that, that's going to affect this cell with the 2 and the 3 in it. So we have to be careful. So let's get rid of this color. All right, so now we know this cell cannot be a 1, and that's going to be a 9. This has to be a 1. I think we can just enter that straight away. But now over here, we have to eliminate the 9 from this cell and eliminate the 3 from this cell. That naked pair is solved for 3 and 9. Now, once we enter the 3 in this cell, that's going to eliminate the 3 from this cell, so this has to be a 2, which means that cannot be a 2. So now we're going to enter the 9 here, a 3 here, a 9 here, and now when we enter this 2, it's going to eliminate this 2 because we have a naked pair of 4 and 2. So this is going to be false, and this is going to be false. So we can enter this 2, and this 3, and this 4, and this 2. And I don't know if you noticed, but when I put this 3 up here in row 5, it removed the 3 from row 5, column 3. So this has to be a 9, and this has to be a 3. Okay, so we're almost done. Now if we look here in block 9, we know this is a naked pair of 4 and 3 and 4 and 3, which means these 2 cells are also a 4 and a 3 and a 4 and a 3. Now we have another unique rectangle pattern. This cell cannot be 4 or 3, or that would create 2 solutions, which would make this puzzle invalid. So the 4 and the 3 have to go in this cell, but because there's a 3 up here already in row 1, this cannot be a 3. This has to be the 4. So now we know the solutions to these cells. This has to be a 4, and this has to be a 3. So now that just solved this naked pair of 4 and 3 over here. This has to be the 4, and that has to be the 3. And that only leaves a 2 for this last cell in block 7. So now in block 4, these 2 cells must be solved for 4 and 8, but because of this 4 over here, this has to be the 8, and that has to be the 4. And now because we put this 8 here, that removed the 8 from row 6, column 9, and now that solved this naked pair. This has to be the 6, and this has to be the 8. And then that solves this cell for 1, and this cell for 6, which solves this cell for 2. And now all of these remote pairs up here are solved, like I said before. This has to be 1, 2, 1, and 2. So now in these 2 cells, they have to be 1 and 9. And because we have a 9 here, this has to be the 1. This has to be the 9. This cell has to be a 1. And now we can look at this as a naked triple in column 4, or we can look at it as 3 full houses in row 4, 5, and 6. And of course, that's easier. So these cells have to be 3, 2, and 9, and the puzzle is solved. That wasn't too bad, was it? So as you can see, when I'm solving the puzzle quickly, I can't keep up with erasing all the candidates, but at home you're going to need to take your eraser, and every time you enter a digit into a cell, you have to erase that candidate from any cell that's in the 3 houses where you entered that number. Got it? Okay, that's going to do it for today. If you enjoyed this video, please click the red subscribe button and the thumbs up icon, and be sure to click the little bell icon if you would like to be notified of new video uploads. And don't forget, if anyone has a puzzle from a newspaper, a magazine, a puzzle book, or whatever that you would like to see me solve in a future video, please send it to me at sudokuswami@gmail.com, okay? As I mentioned earlier, in the next lesson, before we solve our puzzle, there will be a short tutorial on what are called X-wings. This is a very important and common configuration that you definitely need to understand and master, so I hope you will join me for that. Until then, be well and be happy.